In this recording, we're going to extend our knowledge of graphs of polar equations into things called limacons and cardioids. Bet you never heard those words before. They're pretty cool graphs though. And so we're also going to look at what are the applications of these functions or equations outside of a math textbook. So if you'd like to visit the webpage again, tinyurl.com/jdpolargraphs, you will be able to play with this a little bit in Desmos. So in your Desmos site, let me get this set up for you here. You're going to just highlight the purple one. So not the red one. We don't want that circle. We don't want the green one. We just want this purple. So this is something of the form a plus d cosine theta, or in our case, c plus a plus b cosine theta, or we've got the parameters c and d. It doesn't really matter what letters we choose. But I want you to play with those a little bit. This is called a limacon here, and I'm going to grab a screenshot of it. It comes from the French, meaning snail. So kind of a cool word coming from French. And that's a limacon right there. Looks like a little snail, or a slug even. And let me get back to that. So you can play with this a little bit and see the effect of changing those parameters. Okay, again, this was 2 plus 4 cosine theta. I'm going to write that down here underneath our limacon. So let me grab a pen. This is the function r equals, let's see, what was it here? 2 plus 4 cosine theta. A couple things I'd like you to observe here are, okay, that 2, maybe that has something to do with this 2. You could play with that a little bit in your Desmos. And where this 6 is coming from, okay, this sort of maximum value of r here along the polar axis, how is that relating? And is your hypothesis something that always works? And next we're going to look at cardioids. So let's shoot over here. And a cardioid comes from the Greek meaning heart. So we're going to create one of these heart shapes by changing the value of d here to be a 2. Okay, so if this is a 2 and this is a 2, makes a cute little heart there, right? And that is a cardioid. All right, so let's grab a picture of that for our notes. And in your notes, guys, all you really need to do is sketch these out. We'll make accurate graphs in class. But let's just have a couple of examples there and what their equations would be. Okay, so one more time, we'll get that equation. So this was r equals 2 plus 2 cosine theta. Again, see where the value, the maximum value of r here on this equation is, and maybe there's a relationship. Again, play a little bit with Desmos. All right, and so those are the examples. That's a cardioid. This is a limacon. All right, and I want you to see a little bit about where these things occur. Some of you are people that deal with sound. You like to sing, you like to play an instrument, you like to run a soundboard, that kind of thing. Well, check this out. There are things called cardioid microphones. I'm currently speaking into one, okay, as I record this. I'm recording on something called the Blue Snowball Ice Condenser Microphone. Okay, that's its name right here, and that's a picture of the microphone I'm using. Well, let's get into it a little bit about that. So if you go to this web page, if you Google up polar coordinates in cardioid microphones, this is a web page from Int Math, and I want you to check this out a little bit. It's kind of cool. So it has some background into polar graphing, and you can check that out and confirm what you know. There's a lot of ads and stuff, but check this out. This is called the cardioid, all right, because it looks heart-shaped, and it gives us a sense of the function. It could be a sine or a cosine. Other graphs we can have, flowers. I'm not even sure how to pronounce that right there. I'll have to look that up. But now our whole point was we want to know how this connects to microphones. Okay, so an omnidirectional microphone recording from all directions, like a choir, okay, that would be a circle. And we're familiar how to create that circle, right? R equals sine of theta. And you can see for higher frequencies, it becomes a little erratic, but for lower frequencies, it's almost a complete perfect circle. Again, read this website, check it out on your own. Cardioid microphone, again, one that I'm recording with now, is when we only want to pick up sounds from one direction. Like the microphone I'm using, I only want it to pick up my voice, not the other side, not the sound of that, my dog barking on cue right there, right? So notice there's a little space in back behind the microphone that it records, but a spill, it calls it, where it's going to detect some sound. You also have a shotgun microphone. We can create this graph, R equals theta squared. Okay, and finally a bidirectional microphone you could put on the polar axes. Okay, and this would be recording two different sides, like in an interview, right, where you want to record the interviewer and the interviewee. All right, so pretty cool, as it says here. Next time you see a microphone, maybe your mobile phone, notebook computer, recording studio, the shape of its recording pattern is an interesting application of graphs using polar coordinates. So again, back to the snowball. I've got this snowball ice and looked up the owner's manual, and check this out. This is the technical specifications on the owner's manual, and indeed it shows us that cardioid pattern, the polar pattern for the sound pattern. And so check this out. This is a blow up of it, and again we can see the polar axes. I'm not sure why they put their 0 up top, but again, that's how they did it here. And you can see the frequencies are the radii of this polar graph. Pretty cool stuff. Thanks for watching.